I made a quick sketch. We're asked to use the shell method and the washer method. This video is just going over the washer method real quick. So the region that they're asking us to rotate is bound by this curve of y equals 4x to the third, x equals 0, and x equals 2. I guess the assumption is that y equals 0 is another bounding location because we need that to constrain our area. Otherwise, it goes on infinitely, right? So we're looking for this region. We're rotating it around the y-axis. So to do that with the washer method, you want to think about constructing little washers, infinitely small washers. So this is the infinitely small height of the washers. And if you take this off to the side and then flip it around, there's this inner circle, and then there's an outer circle. And we're going to find the two-dimensional area of this outer circle and subtract the inner circle from it. That's making, the washer shape. So we need to have formulas for both of those, for the outer circle and the inner circle. So the outer circle that we're making with each of these infinitesimally small slices is going to be a radius of 2 constantly, right? Because the washer is getting rotated all the way around the y-axis, and it has no height. So if you were to flip it, it would look like this. I guess you can't really draw anything that's two-dimensional by rotating it on the side. But like this part right here, it has no thickness, right? I mean, infinitely small thickness. That's where the calculus magic comes in. So the outer washer constantly is 2 in its radius, because this is 2. This washer that we construct all the way across is 2. This is bound by this x equals 2 line. So the outer washer is going to be pi 2 squared, and then times h. The height of this thing is dy, right? The thickness is infinitely small and dictated by the y-axis. So this is going to be from 0, and then we need an intersection point because we're integrating with respect to y, because y is our infinitely small portion here, right? This thickness is approaching 0. So that's why we're integrating with respect to y, and that's why we need to know where this thing stops up here on the y-axis. It starts at 0. We need the upper bound of our integral. To find that upper bound, we need to plug in x equals 2 into this equation, because if you plug in x equals 2, you're finding out where this curve intersects with this vertical line. So if you plug x equals 2 in here, you're going to get y equals 2 to the third is 8. 8 times 4 is 32. So it goes from 0 to 32 before it finally crosses with y equals 4x to the third. What was I saying? The y equals 4x to the third curve. Okay, so that's the outer shell. Not shell, sorry. That's the outer infinitely small cylinder. And we're going to subtract it by the other cylinder that's happening. I'll draw that with a different color. So here's a cylinder that's infinitely small in its height. And here is the cylinder again. Here's the cylinder again. It keeps changing. The radius here, when it starts, is 0, and it keeps getting bigger and bigger according to this equation. And since we're integrating with respect to y, we've got to rewrite this equation in terms of y. So to do that, you would solve for x. You'd divide 4 from both sides. And then to get rid of a cube, you'd use the cube root, or you could say that's a 1/3 power. So now we have an equation in terms of y, and same limits of integration. And then the volume is pi, and then r is a little more complicated here. It's the cubed root of y over 4, pi r squared, and then our height is dy, right? That's the infinitely small portion that we're talking about. These are right cylinders we're taking out of this, but the right cylinders have no height. Okay, and then the rest is just crunching out the numbers with calculus. This is 4 pi integrating with respect to y. The antiderivative is 4 pi y evaluated from 0 to 32. In this one, you don't really need calculus, right? Because the outer shell is a constant. It's a right cylinder with a volume of pi 2 squared, and then the height is 32. But this is what that looks like in calculus notation. Over here, we need to do some calculus magic. That's y divided by 4 all to the 1/3 power. And so that's being squared. That means we're integrating from 0 to 32. I'll take the pi out because that's just a constant. So haven't done calculus yet. This is y over 4 to the 2/3 because powers on top of powers multiply. So the 2 times the 1/3 power gives us a 2/3 power. And now we can find the antiderivative over here. But plugging in 32, we got 32 times 4, that makes 128 pi. Minus 0, so we'll just forget about that. And then we need to subtract that by the inner area, and that's going to involve the antiderivative. So the 2/3 power is going to increase by 1. It's going to be a 5/3 power. And so to make that be the same, it needs to be 3/5 here. And we need to make an adjustment because of the chain rule. So we're not done yet. If you were to take a derivative of this, you'll see it's not quite the antiderivative, because if you take a derivative, the 5/3 comes down, multiplies to the 3/5, no coefficient like we wanted. But then the derivative of the innermost function gives us a 1/4. So if you were to take a derivative, you'd be multiplying 1/4 the outside. So that means we need to balance that by multiplying 4 here. Now if you take a derivative, the 5/3 comes down and cancels out here. And then take a derivative of the innermost function, the 1/4 comes out and cancels there. Brings us back down to a 2/3 power using the power rule of derivatives. So we got 128 pi subtracted by, plugging in 32 there. I bet we could rewrite that without a calculator. Let's just see if we get a calculator answer real quick. That's nice and clean. It's got 32 divided by 4, and that's to the 5/3 power. That's to the 1.666666667 power, so it's going to be 32. When you plug in 32 in here, divide by 4 and then raise it to the 5/3 power gives you 32. And so that's pi times 3 times 4 makes 12 over 5 times 32. And then if you plug in 0, it's going to make 0. So we've got 128 pi subtracted by 32 times 12, you got 384 pi over 5. Just a little bit more arithmetic. Got to get common denominators. So 128 times 5. That's 640 over 5. And then 640 subtracted by 384. Final answer is 256 pi over 5.